Welcome back, everybody. And the topic today is a follow-up of what we did yesterday, where we discussed the Hohenberg-Kohn theorems, which actually give us a general set of theorems about a many-body system. And what we did was to rephrase the energy as a function of the density. And the Hohenberg-Kohn theorems, although they don't give us an actual recipe, they give us general statements about a many-body system in terms of the density. So if you think back to Hartree-Fock theory and FCI, which we have been discussing, these are normally called wave function-based methods because we start with a wave function. In a certain sense, the wave function here is uniquely defined by the density. The wave function defines the density. So you could also say that this is linked with a wave function, but we have a functional which is an explicit function of the density. And the first theorem says that as we discussed yesterday, that when you have the ground state density of the system, you can uniquely define an external potential, assuming then that there is a part of the Hamiltonian which is universal. And universal means that in this case that you have a kinetic energy and an interaction energy, which you assume is the common feature for the Hamiltonian, the systems we are looking at. And then there is an external potential which confines the motion of the particles. And with the ground state density, you define uniquely this external potential and vice versa. And the theorem, the first theorem was pretty easy to show. The second theorem says simply that if there is such the ground state density, this is the variational minimum of that functional of the energy. And as we discussed yesterday, these theorems, they don't give us any practical recipe. The practical recipe is then given by the Kohn-Sham equations and the family of equations based on that. In the Kohn-Sham family of equations, what we did was to make two basic assumptions. So one of the assumptions is that there is if we're dealing with fermions, a Slater determinant-like quantity, which then defines the density in terms of a sum over the single particle wave function square. And this is something which we also found in the very beginning of the semester when we calculated the one-body density with a Slater determinant. So that was one important point, that the ground state density can then be described by such an ansatz, which often then is reduced to a Slater determinant. And then the auxiliary Hamiltonian, which we're looking at, is then chosen to have the usual kinetic energy and an effective local potential in the density. And I'm coming back today to what we mean by this local density, or local density dependence. So the first thing which we are going to do then is to define a kinetic energy, which then will be explicitly defined in terms of this basis. So let's write down the kinetic energy, the expectation value of that. There's going to be a Hartree term, and then we are going to have a external potential, which is going to confine the motion, plus an exchange correlation part, which we, in a certain sense, is the one where we are going to bake in all the unknown features. So let's just switch back to the whiteboard and try to derive the equations, set them up. And when we are done with that, we are going to start with the third wave function-based method, which is many-body perturbation theory. And when we do that, we're also going to link many-body perturbation theory with FCI and Hartree-Fock theory so that we see the connections between the different methods. But let's wrap up this discussion about density functional theory and just derive the equations. So we are not going to discuss how to solve them, but we just want to derive the equations and then point to some of the specific approximations which typically are made. Okay, so I'm going to switch back to the whiteboard. So if you think of the kinetic energy, we are now going to define the Kohn-Sham kinetic energy. Because keep in mind that previously, the kinetic energy is given by the expectation value of the exact energy, of the exact wave function. But now we are going to define a Kohn-Sham kinetic energy. And this is going to be pretty similar to what we did before when we calculated the kinetic energy of a Slater determinant. So let me quickly remind you of that. So we are going to call this kinetic energy for Ts. This is an expectation value. And we are going to assume that this is a functional of the density. So I will write it below. I'm going to write it like that. And I'm not going to derive these equations because we did that before when we calculated the expectation value of the kinetic energy. And this is simply going to be given by a sum. And if we now have a Slater determinant, as we discussed yesterday, we are summing over all particles of the system. We are going to have a integral, and then we will have the wave function here of r. We are skipping the spin degrees of freedom again. So, but they can easily be introduced because the kinetic energy does not depend on spin. We are having a quantity here where we have put h bar and the charge of the electron, the speed of light, and the mass of the particle equal to 1. So these are normally called natural units. So you don't see a 1/2 times m here and h bar squared. So I'm just taking out these constants. And this is multiplied with psi of I of r. So we did calculate this term when we looked at the operation of a one-body operator. And if you then have a wave function like a Slater determinant, this follows simply from the usage of a Slater determinant, where then this operator here acts on each single particle state. Okay. Then in connection with the discussion of the variational principle, we know that we can actually rewrite the second derivative by using integration by parts and taking the limits when the wave function, where the coordinates go to -infinity plus infinity, because we know that the derivatives have to exist. So we assume also that they go to 0 in the limit of plus and minus infinity, which means that this is something which we can rewrite in terms of a sum of all the particles. And then we have an integral over d of r. And this is the same as phi of I of r. So this acts on particle I squared. So we can write this in terms of the two gradients of the wave function. So it's a standard trick. You do integration by part of this equation here, and then you can rewrite it in terms of two first derivatives. So I'm not going to repeat that. So that's the expectation value of the kinetic energy when we now have assumed that the wave function phi 0 can then be written out like a Slater determinant. So we would have something like a phi 1 of x1 down to phi n of x1, sorry, and then phi 1 of xn, and down all the way to phi n of xn. So if you do that, you remember when we calculated the expectation value of the one-body operator, then we could actually rewrite that as a sum of single particle expectation values. Then there's a Hartree term, which we are going to write down. And the Hartree term is a function of density. And we're just going to leave it as it stands. So this is normally called E Hartree. And that is given by 1/2, and then I have a double integral. And I'm specializing obviously to the Coulomb interaction here. And then we have n of r divided by r minus r prime. And then the Kohn-Sham functional is now given by the following expressions. Kohn-Sham that's given by a functional of the density, which obviously contains kinetic energy. the S here for the Kohn-Sham equations. And then I have the external potential. And again, I'm suppressing the spin degrees of freedom multiplied with N of R plus the Hartree term. And then we have the exchange piece now, which is going to include all the complicated correlations, which we have left out in the description here. And alternatively, there is a term which we normally call for a second energy term, which then could involve the electron-atom interactions, electron-ion interactions, etc., etc. But we're just going to leave that out. Or we also have the, because if you are looking at different atoms in a lattice or molecules, there will be interactions between the atoms as well, the nuclei of the atoms. But we are going to leave that out, and we are only going to look at the electronic degrees of freedom. Now, when we are setting up the equations now, so the Kohn-Sham variational equations, and so this, when we have this functional, we are simply going to use the variational calculus to find the equations of motion. So the Kohn-Sham variational equations, they are now simply given by taking the variational derivatives with respect to the change in the single particle functions, which we then can also translate into the change in the densities here. So the equations then, if we look at them, the Kohn-Sham variational equations, and now we are going to vary these single particle wave functions, because we assume now that the ansatz for the wave function, the total many-body wave function, is given in terms of these single particle wave functions. So what I'm going to look at now is the variational changes for this functional as a function of this delta psi. And these equations are, whether I take delta psi complex conjugate or not, these equations are independent of each other, as we discussed earlier when we set up the Hartree-Fock equations. So this term here is then going to be given, and the kinetic energy has an explicit dependence on these quantities. So this is the variational derivatives of psi of I, and I'm skipping the R dependence here. But then when I look at the next terms, I need to take the derivatives. So I have my external piece, the E external. So we could call this term, which you see here, for the E external. Let me just write it properly here. So we have the derivative of the external part with respect to the density. And I'm going to set up the final equations just in a moment. So we're going to have the E Hartree with respect to density plus this exchange term with respect to density. And this is obviously multiplied with the density, and in the denominator here we have the wave function, which we're looking at. And we want this to be 0. We have also assumed that these single particle states, psi of I, psi of j, form an orthogonal and normalized basis. So this is then valid. We know that the derivative with respect to this function I is the same as psi of I of R. Just remember now that this N of R is actually given by the sum over 1 over N, and then I have a sum here, I equal 1 up to N, and then I have this psi of I like that. That's a definition. When you have a wave function ansatz, we call this the auxiliary wave function, which we assume now replaces the exact wave function. And this is written in terms of the single particle states. And so this would be, if you take a Slater determinant, this will be your one-body density. So that means that if I take the derivative with respect to one of these, I should then just get this term here, which follows from the expression which you have here. Then there are some terms which we can calculate and set up. And then we have other terms which we are just going to leave in terms of some kind of effective potential. And let's come back to that now. So the exchange part, or the external part which we have, is actually pretty easy to calculate the derivative of, because we will have this quantity in here. This does not depend on the density or the wave function. So that means that when I'm setting up this variational derivatives, what I'm going to get now is, for the kinetic energy, if I look at the expression, then the kinetic energy is simply going to be given by this expression here. So that would be minus 1/2. And then I have the derivative with respect to the state here. So if I look at the expression for the kinetic energy, then the derivative with respect to the other quantities are quantities which I'm going to rewrite in a more compact way now. So let's look at the total equations here, because when I now plug in these different terms in the variational Kohn-Sham equations, what I'm going to get then is a quantity which I'm going to define now, the Hamiltonian, minus a Lagrangian multiplier, which is going to be identified with the energy, plus psi of r. And we want that one to be equal to 0. And this hk of s is going to be equal to 1, the kinetic energy, plus a term which we're going to define as the Kohn-Sham potential. So this is an effective potential. So this Vks, when we now take the functional derivatives, is going to be given by this external potential, which we know the expression of. I'm going to have the delta of E Hartree, delta n, and I'm going to simply label that one as a V Hartree. So this is going to define an effective potential, which is going to be local in the density. So we have a delta and then Ex or C, the correlation part of delta of n. And then this term is the term which I'm going to call the exchange correlation potential. So this exchange correlation potential, it's pretty common to approximate that with a local density approximation. What does that mean? So let's just wait a little bit so you get time to write it down. So this effective potential which we have, so the Hartree term is something which we can calculate easily, because the Hartree term, if you scroll back here, that has an expression which depends directly on the density. So that's something which we can set up. But we are just going to, for compactness, we are just going to leave it like this. But this is something we can calculate directly for the density. And the quantity which is more tricky is actually this one. So let's just rewrite now. So what we have is that this Vks is an effective potential, and it's given by the external potential, which we can evaluate. It has the Hartree potential, and then plus the V exchange part. And this is often assumed to be a local density approximated potential. So this is a function assume that this is a function of nr only. That is normally called the local density approximation. So the typical example which we had earlier, like the electron gas, is an example of where we would have an expression which depends explicitly on the density. So C, for example, the electron gas discussion. Results. And what we had then is that the exchange piece, the E exchange, was then proportional to the density to the power of 4/3. So that means that that potential, when you take the functional derivative with respect to density, this potential is going to be given by the density to the power of 1/3. So that's an example of the local density approximation. And in a certain sense, this closes the circle when we started with electron gas, because the electron gas is then one of the many approximations which can be used, and the most commonly used one in the beginning, where you simply take a density dependence which goes like the exchange term from the electron gas, which we calculated, I think, 2 weeks ago. So that means that the alternative is to try to build in an expression where you now have a more complicated density dependence. So a lot of research in density functional theory deals with finding improvements to this function beyond what we call a plain density dependence, where you simply depend on this one. Because if you have a non-local density dependence, you could have then a dependence where your density, if you now remember back to what we defined as a two-body density, you could have a density which depends on R1 and R2. So that is normally called a non-local density because it depends on two coordinates. If it depends on only one of them, like R, which we have in this specific case here, then we typically call this for a local density. So the local density approximation is one of the common approximations which are used to solve these equations. So what we have then, if you look at these terms, this is something we can calculate if we have the density. This is something we can calculate as well. Remember now that the Hartree term, if you go back, contains these two quantities. This is a quantity, if we now have made this specific choice, this is a quantity which we can calculate. So typically then, when you're solving these equations here, which are now the new equations of motion, you end up with an integral differential equation, which is the same or similar to what we had with Hartree-Fock theory. So the difference now with Hartree-Fock theory is that we have a term here which we don't know. So in Hartree-Fock theory, this term was just given by the Pauli exchange term, or just the Fock term in Hartree-Fock theory. Does that make sense? So the difference then is that we are now baking in not only the exchange part due to the Pauli principle, but we're also baking in more complicated correlations. So when I said correlations, the whole thing which we deal with in many-body physics is actually to find the best possible estimation or a way to evaluate the correlations in a many-body system beyond a mean field. Because what we have assumed here now is that there is a mean field which we can use to approximate the wave function and thereby the density. So if we have a typical Slater determinant-based approximation, then we know that the density is given explicitly by this term. When we have that, we can easily calculate this term. We can calculate, obviously, this term because we have an ansatz for these functions. We can calculate the external term here. And the only thing then where we need to make approximations is the local density, beyond the local density. And this is actually where the research goes on in density functional theory. So I hope this kind of excursion into density functional theory allows you to see where the challenge lies and what are the similarities between density functional theory and Hartree-Fock theory. So the Kohn-Sham equations are actually Hartree-Fock lookalikes. Except that now, so when we do Hartree-Fock theory, we do have such an external energy. We do have the Hartree term, but we know exactly how to evaluate that term. And the equations are solved, these equations which we have here, these equations of motion they are solved iteratively in the same way. You start with a guess for the wave function, and then you keep iterating till the energy doesn't change by a constant which you have prescribed. Okay. So let's change gear. As I said, I'm not going to go beyond this. There is a lot of research literature, and if you go into the lecture notes, you will find some of these research directions. But this is where we will stop with density functional theory. I hope you're not too disappointed. Okay, so what we are going to do now is to enter the next topic. And this is going to keep us busy for 3 weeks roughly. And it's also going to be the theme for the second midterm. And this is many-body perturbation theory. So that means that what we have now, till now, is that we have full configuration interaction theory. We have the Hartree-Fock theory. We have looked at the basic equations for density functional theory. So these are normally what we call mean field methods. So I wanted to repeat some of the basics of FCI. And then we are going to look at MBPT, many-body perturbation theory. So let's remind ourselves about some of the things which we have discussed earlier. So if you think back to FCI, the basic assumption is that a state, like the ground state, but you can do this for all the states of the system. So a state psi of I, and this is assumed to be the exact state, can be written as a linear expansion in terms of a many-body basis, which is composed of an orthogonal and normalized computational basis. Can be written in terms of a basis. And if we are dealing with the fermion systems, this would be a Slater determinant of a basis, which we are going to label as a phi of I. And what we did was to rewrite this. And now I'm going to take the example of the ground state, but you could apply this to any state. So psi 0 is the quantity which we normally link with the ground state. So we rewrote this as a psi 0, and we had then phi 0. We used intermediate normalization. And then we had the particle hole expansion. So CIA, and then we have the states phi IA plus AB IJ, CIJ, AB. And this goes all the way up to n particle, n hole excitations. So I just write this as an n particle, n hole here. We had a more compact expression for this in terms of just the particle hole excitations. But what we could do then is that we could actually, if we now have at most a two-body Hamiltonian, when we did that, we could set up the Hamiltonian matrix. And when you diagonalize the Hamiltonian matrix, you get all these coefficients. And then you basically solve the problem. Now, one of the things which we defined then was the so-called correlation energy. And if we now look at the E0, which is the ground state energy, so this is follows from the Hamiltonian acting on psi 0, which is then equal to E0. So this is the exact ground state. And we know that that quantity, when we then had this basis of Slater determinants, this could be written out. So this E0 is something which we could write out as a phi 0. And then we have the Hamiltonian on phi 0. So I should put an hat on top of that, plus the quantity which we call the correlation energy for the ground state. So I'm putting a 0 as a subscript to indicate that this is the ground state of the system. So when we diagonalized, we obviously had all these coefficients. Now this delta E0 with a two-body interaction only is something which we would rewrite, and we found that that could be written as a sum over these coefficients which we get from the diagonalization, and then we had a phi 0, and then we had the Hamiltonian here, but the Hamiltonian minus E0 multiplied with phi of IA, like that. This term here is a term which turned out to be equal to A, and then we had this Hartree-Fock term. So I'm just reminding you of some of the things which we did before. And then we have the next term, which was a sum of IB, IJ. We have this coefficient from which we get from the diagonalization. And then we had phi 0 of H minus E0. And then we had the two particle, two hole state. And this is the case, we have only a two-body interaction at most. If we have a three-body interaction, this terminates at the level of free particle, free hole excitations. And this term here was the same as this matrix element, IJ anti-symmetrized, or integral which is a better name. Okay, does that ring a bell? So this is what you also practiced in the second midterm. So what we have now is an expression here for the correlation energy. So what we are going to do now is actually to use approximations to the full problem and find expressions for these coefficients. So let's just rewrite this now in terms of these specific integrals. So this is equal to the sum of AI, CIA, and then we have A of F of I. So what happens if I have a Hartree-Fock basis? With that specific term? It's zero, exactly. Because you remember in Hartree-Fock theory, this is the overlap between the zero particle, zero hole state, the ground state ansatz, and the one particle, one hole states. And that is zero if we have a Hartree-Fock basis. So if we have run a Hartree-Fock calculation, then this is zero if we have a Hartree-Fock basis. Now, if I have a density functional theory basis, this is not guaranteed. But you could solve the equations, the equations for the Kohn-Sham equations with that requirement. And then we have a term which comes in here of A, B, I, J. And this is what we developed earlier this semester. And that contains this integral over the two-body interaction of IJ. And we write AS to indicate that these are anti-symmetrized matrix elements. So this is an extremely compact expression. And if you can diagonalize exactly in the basis you have chosen, then you have the answers. Now, when we are going to do many-body perturbation theory now, we are going to show that, for example, many-body perturbation theory. So I just want to give you the results which are coming and which we are going to derive. So if I do that to second order in the interaction, to second order, so this is to second order in the interaction part of the Hamiltonian. Then what we are going to get is that this coefficient is going to be exactly equal to the same integral of A, but since this is a coefficient, it has to be dimensionless, and this is divided by the single hole energy minus the single particle energy. So this is to second order. And clearly there will be similar contributions to third, fourth, fifth, and higher orders, because this is going to be a Taylor expansion in the energies. In our case, the energies which we're going to expand around are going to be these energies here. The other term, which we have, this term here, is going to be equal to IJ, V, AB, anti-symmetrized, but now divided with epsilon I plus epsilon j minus epsilon A minus epsilon B. Then I should also keep in mind that there are higher order terms. Mind that we have higher order terms. Because we are going to do a Taylor expansion. But what you see here is that if we stop to second order, we get a recipe to evaluate the coefficients you would get from diagonalization. So you can view many-body perturbation theory as a recipe by which you can, in a systematic way, build up these coefficients which you would get from diagonalization. So if the problem to diagonalize is too large, then this is a recipe where you now can just focus on the ground state or some few selected low-lying states. And then by perturbation theory, you can then find expressions for these coefficients order by order. So this is the kind of overarching view on what we are going to do now. Does that make sense? So we are going to show that these expressions are the expressions you will get after we have derived the basic equations for many-body perturbation theory. So what you're starting with is obviously a many-body basis, but we break everything down, as we have always done, in terms of single particle wave functions and integrals over either two-body or one-body interactions, simply because we have built up the many-body basis in terms of a single particle basis. If you hadn't done that, then the equations would have been much more complicated. You would actually have to evaluate multidimensional integrals, because then you have a wave function which you cannot break down into a product of single particle wave functions. So this is going to give us a systematic recipe, which we, by order, can then improve the quality of the calculations. And in some cases, like what you will see also in the midterm, you actually have the possibility, order by order, to compare with the exact coefficients. And that's pretty useful. There's something you can see from this expression. So when I say order by order, so this will be to second order in interaction, because we have the interaction V here and the interaction V there. But if you look at the wave function, if we now just go back to what you have here, you see now that the wave function here, this is the wave function, depends on these coefficients. So that means that if we think in terms of the wave function, that term would be to first order for the wave function. And then that means that there is going to be a perturbative expansion also for the wave functions. And order by order, we can then build up the coefficients CIA, Cij, AB, etc., etc. But when you look at these equations here, the equation which I gave you here, I hope you can, from the intuition by looking at these expressions, you can say where the potential problems are in perturbation theory. So we are now going to have an expansion in terms of these quantities here, which are going to define the coefficients. So if I'm making a Taylor expansion in terms of these terms, so you could think of these as the x's you're making the Taylor expansions in. So what kind of problem do you see if you think of a Taylor expansion? So what should the ratio be in order for a Taylor expansion to converge, so you could truncate at low orders, for instance? So how do you think the ratio should be between the interaction and its denominator? Can it be larger than 1, or should it be less than 1 when we're looking at a Taylor expansion of a specific quantity? What is your intuition about that? Yeah. Yeah. It's because the kind of expansions, many of the expansions we will look at are actually typical geometrical series. And then clearly for that to converge, this ratio should be less than 1, the absolute value.
But I'm just wondering, like, aren't what you've written there, like they first for the coefficients and not the variable we're expanding? Right?
So I am expanding around these terms here, the ratio between this term and that term.
Oh.
So that's going to become the expansion parameter. So what I wanted to give you now, before we derive the equations, I wanted to give you an example which we can solve. It's going to be a 2-by-2 problem. And if you understand that problem, you have understood the basics of many-body perturbation theory. So this simple example conveys much of the type of problems which you face in perturbation theory. So let's look at these simple examples as an intermediate step before we begin with the formal derivation of many-body perturbation theory. And hopefully that example is something which you can keep with you because it simply shows you the kind of problems which you get when you now diagonalize. And this is actually an exercise which you will see next week as well, because you can diagonalize it exactly and you can find the coefficients. So let's just look at this exercise which you will encounter next week. So the simple example which we are going to look at, so we are going to have a simple example as an intermediate step. Before formal derivation of the equations. So this simple case is going to be a system where we have only 2 states. So we are going to define a one-body part of the Hamiltonian, which now contains a sum P from 1 to 2. So P equal 1 up to 2, only 2 states. And there is a single particle energy. You can think of this as a single particle problem or a many-body problem. And then we have an interaction piece, which is given by G, and then I have a sum PQ, and then I have AP dagger, AQ. And I'm going to assume then that there is a 2 states, epsilon 1, which is lower in energy than epsilon 2. So these are just choices which I'm making now. Then I'm also going to assume that there is a basis. So O and B basis, and I'm just going to call that O and B basis for 1 and 2. And obviously, if I take 1 and 2, that is going to be equal to 0. So we are going to assume that this is our computational basis. And so in more general terms, what we have is just I and J equal delta IJ. Secondly, then we know that the completeness relation is given by the outer product of this vector 1 plus the vector 2 here. Secondly, I'm going then to obviously assume that these basis states, 1 and 2, are eigenstates of H0, as we did when we constructed a Slater determinant. So I'm simply now going to assume that H0 acting on the states I is given by epsilon I times the state I. Secondly, I'm going now to assume that I can define a projection operator, 1 of 1, and another projection operator, which is 2 of 2. And we know that these operators are so-called idempotent, which means that they are equal to the squared. And we also have that Q squared is equal to Q. It's pretty easy to show, and we discussed that in the very beginning of the semester. And furthermore, P and Q commute. And then we can just make a simple example now where I say that this state 1 is just A1 dagger acting on 0, and the state 2 is equal to A2 dagger if we are dealing with this in second quantization, and 0 is just a true vacuum here. And then we can set up the Hamiltonian matrix. So we see quickly then that if I take the expectation value of 1 with H0 of 1, this gives me simply epsilon 1. And similarly, if I do 2 of H0 and 2, that gives me epsilon 2. If I take P and Q here with H1, the HI, the interaction piece, this is going to give me a term which is just going to be given by G. And P can be equal to Q or different from Q. So that means that my Hamiltonian matrix now, we're not going to calculate this because the only thing you need to do is to set up the expectation values. So if I take 1, and then I have a sum of a P and Q, and then I have the operator, I have this constant which I put outside G, then I add AP, AQ of the state Q, for instance. That is the same as us calculating the expectation value. I have the sum of a P and Q, and then I have A1 dagger, AP dagger, AQ, and then I have it's not a dagger here, it's this one. And then I have A2 here, acting on 0, multiplied with G. And we see now that the contractions which I can make are typically of the type where I have now this contraction and that contraction. And that gives me now that I get a Kronecker delta, delta P1, and delta Q2. So it's pretty easy to calculate the different contributions to the Hamiltonian matrix. So if I do that, I'm going to get the Hamiltonian matrix. So this is the Hamiltonian matrix, which is then given simply by epsilon 1 plus G. And then I have G, and then I have G, and epsilon 2 plus G. And then we know that the characteristic polynomial is simply given by the determinant of this equal to 0. And after the break, we are going to set up the equation. And I hope you don't get offended if I don't go through the details of solving a second order problem. I'm just going to state the eigenvalues, and then I'm going to make a Taylor expansion of the square root. And that Taylor expansion, which we're going to make, is going to be the same which we would get if we do many-body perturbation theory. So that's a pretty neat example here. But let's take a break here and be back in 15 minutes, if it's okay.
Jo da. Jeg tenkte litt på det når det gjelder sånn DFT.
Ja.
Så du har egentlig bare brukt det som en svart boks, altså som du skulle koble opp til molekylærdynamikk og sånn.
Her nå, ja. Så det er jo det sånn at man har en liten sånn boks inni den klassiske.
Og da har du ikke gått gjennom noe særlig teori heller, eller noe sånt?
Nei, planen har vært egentlig at jeg skulle klare å bygge opp programmet skikkelig før kurset her. Sånn at jeg bare kunne fokusere på teorien. Men så har jeg ikke fått til å satse inn over det teknologiske programmet. For til å linke de to sammen. Så det har vært, ting er mye litt trukket.
Så egentlig denne kurset setter FYS med den 4M10. Veldig nyttig for det.
Ja. Og spesifikt på det.
Jeg vil godt snakke med Gunnar som sitter på kontoret.
Ja.
Og de har undervist i det kurset.
Ja, ikke sant.
Så egentlig, de bruker jo mye lengre tid på det vi har gjort nå, fordi vi har jo diskutert at vi får flytte.
Ja.
Og vi har studenter som er mye mer matematikkfag generelt. Fordi det er noe mange mener, så det er
Stemmer. Så det er lagt opp til det, og mer fysikk.
Og Gunnar har jo brukt 6 eller 7 dobbelttimer på å gå gjennom det som vi har gjort i løpet av det. Stemmer, har jo brukt det tidlig også. Men vi bruker også mye mer tid på å diskutere lønnsing og følge litt til.
Men er det jeg skjønner sånn at vi får en Kohn-Sham-anvending, det er en del av density version theory, eller altså de på en måte...
Nei, det er jo den måten vi løser det i praksis.
Ja.
Fordi du vet jo ikke, fordi egentlig så er det, hvis du skulle løse problemet, så er det akkurat som å løse et komplisert problem.
Ja.
Så da gjør en approksimasjon, og du antar at du har en determinant som beskriver systemet.
Stemmer.
Så det er jo tilbake egentlig til det, som vi heller en slekter determinant for Westman, men bare til de uttrykker det.
Ikke sant, ja.
Og så antar at det finnes en funksjonal som tar for seg all den kompliserte reelle som du får i livet ditt. Det bakes inn i exchange correlation.
Men det er utelukkende for elektroner.
Nei. Det er også fryktet for kjerner, de har fryktet for mange andre systemer, men det er mest i systemer hvor du har polenvekstvirkning til et stort nedslagsfelt. Så det for atomer og molekyler, og for faste stoffer, materialer. Da plasserer du disse elektronene i en gitt struktur, og så har vi ionene som sitter fast i sine posisjoner, altså det du ser på. Og så setter de opp et effektfelt som disse elektronene ser. Og så begynner du å simulere med 10.000 av det. For det klarer ikke med noen metoder som den eksakt generalisering, men nødt til å få det på noen dimensjonalitetsproblem. Og da har du liksom DFT som ligger et feltmetode, det er sånn en vei mot 10.000. Og hvis du går utover 10.000, så må du gå til molekylærdynamikk.
Stemmer.
Og da må du skvise bort til kvantemekanikken, men da kan du bruke DFT til å lage et effektivt klassisk potensial.
Stemmer.
Og da skviser du kvantemekanikken.
Ja.
Og de som gjør det, de tjener masse penger.
De gjør det?
Ja, fordi de jobber jo blant annet med det, altså. Det med farmasøytisk industri. Så den overgang i DFT, hvor du kan gjøre mikroskopiske simuleringer, og definere et klassisk potensial som går inn i molekylærdynamikklinjer, som bare er newtonske linjer. Da lager det potensialet det, sånn at det gjenspeiler det fysiske systemet. Det er det andre pengene ligger.
Ok, det gjør det, ja.
Det er jo firmaer og forskningsgrupper som er spesialisert på det. Det eneste du får. Du får jo alltid uttrykkene. Du får bare en kode, en binærkode, som du har koblet opp. Det har du sett når du liker lamps.
Ja, absolutt, ja.
For noen av de potensialene har du fine analytiske uttrykk for.
Stemmer.
Mens i andre tilfeller så er det bare en kode koblet opp.
Ja. Ok, så du ser altså den minasjonen på...
Det er stor industri det også.
Skal man få koblet opp, så er det 2 kommer, det var masse der, og...
Så en av de store anvendelsene av DFT er mot farmasøytisk industri. Og molekylærdynamikk.
Ja, for det er jo skjønt, altså mye av det her, det lille amerikanske voksen, det er ofte å se på dokk. Altså det er på en måte, virkemidlene binder seg til programmet. Så da er jo det...
Det er noe sånt det du ser på.
Absolutt, ja. Så har den kompetansen.
Ja, det er tydeligvis ikke dumt. Ja, Altså, Anders har jo en kollega i USA som sa at han hadde sluttet helt å hente inn postdocs.
Ja.
Fordi de går rett ut i industrien og tjener 3 ganger eller 4 ganger. Fokuserer bare på doktor og sånn.
Ja, ikke sant. Men hva kan du forklare forskjell på postdocs og doktorgrad?
Postdoc er jo rett til teori.
Ok, ja.
Så det er jo en form for trening hvor de liksom kvalifiserer til stillingen. Da er vi mer selvstendig forsker.
Stemmer.
Så
jeg har forstått at det i mange sammenhenger så lønner det seg ikke ta en doktorgrad, men her hører på dette feltet høres det ut som at
det svinger vel.
ja.
Tingen at i dag i Norge så er jo både en postdoc og en PhD lavere enn medianlønna i Norge.
Og det er det. Så da må man litt utlandet.
Nei, det er rene lavene.
Ja.
De eneste landene hvor du har en decent lønn er jo ikke som stipendiat, for det betaler de fleste landene dårlig. I Italia for eksempel er jo månedslønnen 1000 euro i måneden. Så de nordiske landene, de som betaler best på PhD, men når du går på postdocs-nivå, så er det Danmark betaler godt, Tyskland og USA.
Ja.
Men det er ikke derfor vi er for det mot.
Ja. Det er en liten balanse.
Ja, det er jo det. Altså. Nei, men i de fleste land så er en doktorgradsstudent spesielt godt. I Norge så har vi vært en regel at du skal ha samme lønn som den dårligst betalte offentlige ansatte med den samme bakgrunn.
Ja.
Og det er en skolelærer.
Det er ikke sant.
Men doktorgradsstipendiat i Norge ligger omtrent på sånn begynnerlønn til en lett og videregående skole. Det var samme bakgrunn med en mastergrad. I mange land så er lønnen veldig lav i akademiske land. Dessverre.
Ja. Hva var det som skjedde? Det var en gang som budgetallet der. Så får det mye av det.
Men det var jo mange feil stillinger. Og så er jo også lærerne rimelig lønnsledende. Så har de bare sagt han mer og mer. Dessverre.
Det er jo bare det at man på et eller annet vis har sett at det er ikke gjenstand for at det er samfunnsperspektiv. Man ser ikke verdien av
det pene som litt akkurat så tar det da passe for å bruke som skjedde igjen. Du får ikke av det.
Men det hjelper jo ikke det så som jeg ikke har forstått.
Du bare satser på at du har litt sånn hobbyvirksomhet. Hobbyvirksomhet, samme som tech-industrien, det er jo masse hobbyvirksomhet. Som jeg startet med liksom satt opp for folk som tar sine poststudies. Det er vedlikehold på fritida, og så bruker du det i det private da, i jobben sin. Så liksom, det er liksom, noen steder som har noen sykehjelpsstudies, alle bruker det. Og så får de litt betalt av Gud og sånt, men ikke mye, bare får de resten med forskning og vedlikehold. Men ikke selv liksom lage det til det her. Men du får litt flere i forskning. Og jeg får skulle sjekke ting, forhåpentligvis.
Nei, det er alltid en balansegang på hvordan
det er ikke bare hele oljeindustrien, det er masse, de har litt forskning. Bare væske i porøse medier og så videre.
Ja. Så er jo livet litt å finne sine lidenskaper og sånt. Og det er jo en veldig god venn og nabo som er snekker, og det er hans lidenskap. Noen pilarer av vitenskapen er for det er veldig godt. Det å finne fram til hva du liker best, og hva du føler fint, altså, det er jo, ja. Altså, mastergraden er jo et steg i den retningen. Ja. De fleste håper med mastergrad at de fleste utvikler en dypere innsikt om seg selv. Og finne ut at nei, dette klarer jeg, dette liker ikke. Jeg klarer å løse problemet, klarer å definere problemet. Så jeg håper at man går opp med litt større skjønn.
Kombinert. Ja. Okay, so I'm going to put back the recording. So for those of you online, I'm going to start again. Okay, didn't I stop the recording? I think it's been going on here. Okay, so before the break, even though the recording from the break is also on because we didn't stop the recording, we set up this simple problem, which is actually a two-level problem. And we have a Hamiltonian matrix, which we know how to diagonalize. And this is a matrix where we can both find the eigenvectors and the eigenvalues easily. So the eigenvectors, we will then have a lambda 1, 2, is then obviously given by an epsilon 1 plus an epsilon 2 divided by 2 plus g plus minus. And then I have epsilon 1 minus epsilon 2 squared divided by 4 plus g squared. So what I'm going to do now is to simply rewrite that the second term, if you look at the square root. So I can now actually rewrite this square root here. So let's just expand it. We can Taylor expand it because what we had originally, so let's take this term here. And that term is a term which I can rewrite as an epsilon 1 minus an epsilon 2 here, multiplied with, and I'm just going to rewrite parts of it in terms of, so I'm going to skip this factor of 4 in front of the term, but I will actually rewrite it like this, epsilon 1 minus epsilon 2 squared. And then we know that if we now define x to be equal to 2 times g divided by epsilon 1 minus epsilon 2, if we square that one, we can then simply Taylor expand the square root. And when you Taylor expand the square root of 1 plus x here, this is going to be equal to 1 plus x half minus x squared divided by 8 plus x cubed divided by 16 plus to infinity. Okay, so what I do now is that I can write an expansion in terms of the ratio between the interaction between the states and the spacing between the states, epsilon 1 and epsilon 2. So if I do that, then I will get two energies. So if I look at the first energy, I will have an epsilon 1 plus g. So this leads to, if I now insert this expansion, this is going to go like minus g squared divided by epsilon 1 minus epsilon 2 plus g to the power of 4 of epsilon 1 minus epsilon 2 cubed and plus. So this is going to be the lowest lying state. So remember now that when I acted on with H0 on that state 1, that was the same as epsilon 1 times 1. So that would be what we normally call the non-interacting or unperturbed. It's not perturbed by the interaction because we're going to look at the interaction as a perturbation to the system. So we will often call this for unperturbed. So this is the non-interacting energy. And what we get now is a correction to this energy due to the interaction. And if I sum these terms to infinite order, then I'm going to get the same result as I had before when I diagonalize. So if I sum these terms here in this square root to infinite order, then I should obviously get back to the expression which you see here. Okay? So if we now look at the different terms which we have here, so the first term is going to be when we look at many-body perturbation theory, MBPT, and we are going to derive this in the exercise next week. So this will be many-body perturbation theory to first order, and that is to first order in the interaction. Then, and you see that this, if G has dimension energy, which is pretty common, then this has dimension energy, this has dimension energy. Here I get energy squared divided by energy, dimension energy, energy to the power of fourth divided by energy cubed, also energy. So this has the right dimension when you look at the quantities. So the second term which we have, this one, is what you will often see in the literature being called MBPT2. So that means obviously to second order. So what you also notice here is that we have no third order term. And we're going to discuss that next week, why we don't have a third order term here. So this is just something which happens due to this specific model which we have defined. So MBPT3 is 0. So we have no third order term. But then we have a term to fourth order in the interaction. So that will be fourth order. And this obviously continues to infinite order. Now, clearly, if the ratio between G and epsilon 1 minus epsilon 2 is less than 1, the hope then is that we can truncate at a lower order, that we don't need to evaluate terms to higher and higher orders. If that is not the case, if this ratio here is larger than 1, then we need actually to sum all terms to infinite order. So perturbation theory, what we are going to do now is an expansion in terms of the interaction divided by the energies. And the expansion then converges if this ratio between these two quantities is less than 1, typically. So this simple example, which you see here, conveys the basics of many-body perturbation theory. Was that pretty clear? So we're going to play around with that exercise, this simple example later. Now, what we need to do now is do the formal many-body theory. So let's do that. So formal MBPT. Actually, there are two variants of many-body perturbation theory. One is named after Wigner and Brion. It's called Brion-Wigner perturbation theory. And another is called Rayleigh-Schrödinger perturbation theory. And that is the most commonly used in the literature. But let's derive the basic equations. So just to keep the link with FCI. So now what we are doing is to make an approximation to FDI. And where the approximation to FDI is going to be given by a expansion in terms of the interaction divided by these energies. So let's see and remind ourselves about the things which we did with FCI right before the break. So we would then have a wave function psi0, which is given by phi0 plus these different higher order terms. And let's now label them as particle hole, where this starts from one particle, one hole, two particle, two hole, etc., to n particle, n hole. And in principle, we have an infinity of such guys here. So these are the coefficients, and then we have a n particle, n hole state here. That's a little bit different from what we had before. Another thing which we're also going to assume is that we are going to use what we call intermediate normalization. So that means that we just reshuffle the strength for the interaction to the coefficient CHP, or the strength of the normalization to the other coefficients. So we are going to assume that phi0 with phi0 is equal to 1. And then we also set that psi0 with phi0. And we did that when we looked at the FCI calculations. Also, what we are going to do now is to, instead of using this type of notation here, we're just going to make it a little bit more compact. So I'm just going to rewrite this one now in a little bit more compact way. So I'm simply going to write this as a phi0 plus, and it's going to have a sum over states. And these states are going to run from 1 in principle to infinity. But I'm going just to call this upper limit for d, and in principle this is infinity. There is a coefficient c of m, and then we have these determinants or these many-body wave functions like that. So this is just I just want to save notation here. Yeah. So this is actually psi0, like that.
I'm talking about the intermediate normalization.
Yeah, so because you have this intermediate normalization, you can require that one, because that means that the coefficient here, because else we would have to carry with us a coefficient C0. But what happens then when you do the normalization, you just reshuffle everything into these coefficients here. So we use that as a cheap way of getting rid of C0 here. You can keep C0 if you want to, because when you diagonalize, C0 is there. So this is just a way to compactify the notation and simplify things a little bit. So what we also need to remember is that H0 acting on phi0, this is something we assume now is given by an eigenvalue problem where we have this epsilon 0 acting on phi0, like that, or multiplied with phi0. And we have the full Hamiltonian acting on psi0, which is equal to E0 multiplied with psi0. So this is the ansatz, and we have a similar equation for all the other Slater determinants we can make. And this is the exact ground state of the system, GS. And keep in mind that you can replace psi0 with any other state of the system. And the Hamiltonian is then written out in terms of an H0 plus this H of I and I for interactions. And I should put hats on all these quantities here. Sometimes I forget to put on the hats here. So if you now multiply, take the equation here and multiply with phi0. And this is actually what we did when we calculated the correlation energy. So we know that this one is simply going to be equal to E0 because we're using intermediate normalization. And then I can rewrite that term. So if you look at this specific term which we have here, this is going to contain now, if we look at this equation which we put up, this is the same as phi 0 of h of phi 0 plus, and then I have the sum over all these coefficients n equal 1, and in principle to infinity, and then I have the coefficient c of m, and then I'm going to have phi 0 of h with phi of m. And this could be the particle-hole correlations which we have defined. And in our case, this term is a term which we are going to, if we write it out in full detail, it's going to contain all these particle-hole excitations which we have, of phi 0, of h, of phi, of h of p, like that. But now I'm just writing it in a little bit more compact way, and I'm not keeping these p's and h, I just have a subscript n here. Okay, just to simplify the notation a little bit. We know that this term here, this one, this defines what we call the correlation energy. This is a quantity which we also have defined earlier, and we call this for the E0 of reference. And remember now that this phi 0, that could be a Hartree-Fock wave function. It could be a Kohn-Sham based Hartree or reference state, or it could just be the reference state, which is constructed from the wave functions which enter phi 0 here, and which are then the solution to this problem. So this is something which we just leave there as it is. So just keep in mind that this could be a Hartree-Fock ansatz, it could be a Kohn-Sham based ansatz, or it could just be an ansatz which is based on the basis functions which are eigenstates of that problem there. Okay, so if I now look at these expressions, so what this is, if I just rewrite it, so this gives us that we have E0 minus E0 ref, and that is given by the sum over m of c of m, and then I have the phi 0 of h, and then phi of m, like that. Okay, in perturbation theory, we're going to change this a little bit. So let us now look at the equations which we have put up. And when I now set up the equations here, I'm going to get, if I look at the Hamiltonian, I have an H0 plus an H of I times, so if you look at this expression here, times psi 0. This is going to include a term which now will contain this epsilon 0, as we have said before. So we will have a phi 0, but just keep in mind now that phi 0 of H0 of psi 0 is the same as psi 0 of H0 of phi 0, and that is the same as this epsilon 0 here. So I can rewrite these expressions in terms of one term which now contains epsilon 0 plus this term which goes like phi 0 of H interaction of psi 0. So the this expression is obviously going to be equal to E0. So I can now write out E0 minus epsilon 0, which is then equal to this phi of HI of psi 0. And that is normally the one which now defines the correlation energy in perturbation theory. So just keep in mind now that what I've done is a little bit different from the FCI correlation energy. So the quantity which you had here is delta E 0. And the expression is pretty common from what you get from full configuration interaction theory. And this is normally the one from FCI. So this quantity which you see here defines delta E0 for many-body perturbation theory. So it's a little bit different because when we did the FCI calculation, we had the full reference energy, and that full reference energy is the expectation value of the Hamiltonian, the full Hamiltonian. Now we have singled out the non-interacting case. And what we have done here is on the left-hand side, no, on the right-hand side, we have something which depends only on the perturbation or interaction, which is acting on the system. So this is normally called the non-interacting energy. So this is just a slight reshuffling of the terms, because we want to now make an expansion in terms of the interaction. So we single out the non-interacting piece, or the unperturbed part, and then we have one which is given by the perturbation. Okay, just a slight difference in the way we define the correlation energies. You can obviously always pick out, because if you look at this expression here, so let me just write this down. If we take that one, so let's just rewrite it here, and you will then see the connection between what we did for FCI and what we now are setting up for perturbation theory. So we have minus epsilon 0, and this is equal to phi 0, and then I have this interaction term, and now I'm setting up phi 0, obviously, but then I have the additional terms over m and this coefficient c of m, and then I have phi 0 of h of I of phi of m here. So if I now shuffle this over to the other side, then you will see immediately that we have back the standard reference energy. So if I plug this one over here, that would be the reference energy, which we have defined before. So just remember now that what we defined as the reference energy was then phi 0 with the full Hamiltonian. And that is equal to phi 0 of h0 of phi 0 plus phi 0 with the interaction piece. And if we connect things here, then this one is nothing but that, and this one is nothing but that. Now, the reason why we make this splitting is that this is actually first order in the interaction in h of I. And that's why we make this split now, because we want to make an expansion in terms of the interaction. So that's a change from what we did with full configuration interaction theory. Okay? So just a reordering of terms, nothing else than that. But let's then define some intermediate steps here. So we define them, these operators. So I define this projection operator, which is phi 0 of phi 0. And then I have my next operator. I should also remind you that this is the case. And then I have Q, which is simply going to be given by the sum over all the other states, M1, up to D here, of phi of M, of phi of N. And Q squared is equal to Q. And what we also have is that these two guys commute. That Q didn't come out nicely, so let me just rewrite it. P and Q, this is exactly equal to 0. Okay? So what I'm going to do now is to manipulate the expressions. So the expression which we had, which is this one, which you see here, I'm going to rewrite this in a much more complicated way. So when I've done with the derivation, you may ask yourself, what's the point in doing that? But hopefully you will see that after when we start developing the equations, that this is actually a very handy way where we can single out term by term in a Taylor expansion. So what we're going to do now is simply to do a rewrite. And the kind of rewrite we're going to do, we start with psi 0, which is equal, obviously, since this is the given by the completeness relation of P plus Q times psi 0. Because P plus Q is actually equal to the identity. So that means that I can rewrite this expression as phi 0 plus Q times psi 0. So if we then look at the Schrödinger's equation here, what we have, if we look at that one, so we have an H0 plus H of I acting on psi 0. This is the problem we want to solve. And this is equal to E0 of psi 0. Now, what I'm going to introduce now is a variable. So introduce, which I'm going to add and subtract. So I'm just adding 0. Introduce W times psi 0. And I'm going to make an expansion, a Taylor expansion, as a function of this variable omega. Or W. I think it's a W. Now let's call it W. Okay. So I can then, if I introduce that one, I can add and subtract, and then I shuffle over H0. So I have H0 multiplied with psi 0. And that is equal to this variable omega minus E0 plus H of I multiplied with psi 0. So what I'm going to do now is simply to rewrite the equations so that I can express this in terms of this term omega minus H0. So what I'm going to do now is I'm going to assume that this one, the inverse of that, because keep in mind that these are matrices in principle. We assume that this one exists. Okay? That's an important, this is called, it has actually a name in the literature, it's called the resolvent. You know that you can set up Schrödinger's equation in terms of you inverting a matrix. Now, just to give you a digression here, if you look at Schrödinger's equation, you can obviously, instead of calculating this as a differential equation or whatever, you can actually calculate the inverse of the full Hamiltonian here. That's called the resolvent. That leads to the theory of Green's functions. So the reason why you stick with this H0 here is that this is a known operator, and you know also the solutions of that. So what we also have to keep in mind now is that this operator P, and this is something which I leave as a small exercise, which is actually easy to see. This operator commutes with P and Q. And this is simply because H0 acting on these states phi m is given by an epsilon n of phi of m. And these operators like P is given by phi 0. And then it's easy to see that these operators commute, whereas Q, as we said earlier, is given by a sum from m equal 1 to infinite dimensionality of phi of m of phi of m. Now I'm going to write this in a slightly different way. So the matrix which we have, H0, is only going to give us elements along the diagonal. But I'm going to write this omega or W. I'm going to write it in this specific way, like that. Now, there are some important aspects here, and that is that if I now calculate Q divided by omega minus H0, this is the same as Q, since Q squared, and since it commutes with H0, and this omega is just a number, I can write it like this. But since Q squared is equal to Q, I can write this in a more compact way. So this is a kind of sloppy notation, but which makes it a little bit easier to write down all the equations. And this has to do with the fact that the Q and P commute with H0. So if I Taylor expand this, I will have H to the power of 1, H0 to the power of 2, etc., etc. And then when it acts on this one, it acts on states which are included, which are actually eigenstates of this H0. So this kind of notation here, although I don't like it that much, is the kind of notation I will use. But in principle, what we are dealing with is the inverse of a matrix, which I write in this notation here, which makes every mathematician actually dislike me. But you will see this often in many, many physics textbooks, okay? So let's continue, because if I have that, you see now that if I multiply on both sides, I assume that it exists. If I multiply on both sides here, then I get psi 0. And then I can pick out the term which is linked with Q here, because there's a term which goes like phi 0 plus Q. So what I could do now is if I multiply this expression here with Q, so if I look at the term, which now includes, let me just find my note here. So what it means then is that I can now rewrite this Q acting on psi 0. This is now going to be equal to Q divided by omega minus H0 multiplied with the term which I had here, omega minus E0. So everything I do now looks like a horrible complication of the original problem here. So if I bring everything back and include the whole psi 0, this is going to be equal to phi 0 plus this term Q of omega minus H0. And then I have omega minus E plus this term multiplied with psi 0. So this looks like an horrible overcomplication of Schrödinger's equation. But the whole philosophy now is that we can solve this iteratively. And then we would start with a guess on the right-hand side for psi 0. And the obvious guess is actually to start with phi 0. And then we have the first iteration. So the typical way for solving this type of equations is to solve them iteratively. So you start with phi 0 on the right in the equation here, on the right-hand side. So that gives me psi 0, 1, which is then given by phi 0 plus this term Q of omega minus H0 of omega minus E plus H of I multiplied with phi 0. Then I insert that one on the right side again, and then I keep going. And if you keep going like that, you can sum these contributions up, and that means that you will get a term, a final term which looks like as follows. So what you get then is the standard perturbative expansion for the wave operator. So we'll get then for the ground state of the system, the ansatz here, and this is formally an exact equation, n equals 0, and in principle this goes to infinity. And then I have my operators Q divided by omega minus H0 of omega minus E plus H of I. And this is to the power of n multiplied with phi 0. Now, the problem now is that these expressions here contain an unknown quantity. So E0 is unknown. We are assuming that this term is known, obviously. This is the interaction. This term is also known. And the same apply to this one, known, etc., etc. So there are now different ways by which you can start solving these equations. So one of the approximations which is done then is what is called Brieux-Wigner perturbation theory. Many-body perturbation theory. In that case, we make a choice. And we make the choice that omega is equal to E0. Okay. Now, the other choice, which we have, is normally called Rayleigh-Schrödinger perturbation theory. And in Rayleigh-Schrödinger perturbation theory, Rayleigh-Schrödinger then we replace this epsilon with E0, which is the unperturbed energy. So keep in mind that E0 is a quantity we know how to calculate that, and that is equal to epsilon 0 times phi 0. Now, what you see now is that you get some simplifications, but in both cases, you have an additional dependence on the unknown parameter. So if I take Rayleigh-Schrödinger perturbation theory, I'm plugging in something known here and something known here, but then I have this one. And this is something which we need to deal with next week. But then if I do Brieux-Wigner perturbation theory, then I have E0 here, which is the unknown quantity, the energy, the exact energy. But then I get rid of it from here. Now, if you look at the equation you have, if you now want the energy of the system, what you need to do then, if we now take the expressions which we put up, if you now multiply with phi 0 from the end with hi with psi 0, this is nothing but what we called for the delta E in many-body perturbation theory. And if I plug that one in the equation for the wave operator, then I have n equals 0 to infinity, and then I have a phi 0 of h of I multiplied with q divided by omega. Actually, this is a general expression, multiplied with omega minus E0 plus hi multiplied with phi 0. So let's now look at the explicit implementations of Brieux-Wigner and Rayleigh-Schrödinger perturbation theory. So let's just do Brieux-Wigner BW perturbation theory. And in that case, we're going to put this variable omega equal to E0. That means that this delta E0, and now I'm going to skip many-body perturbation theory, because now the delta E, the correlation energy, is for perturbation theory. So that is going to be equal to the sum over n equals 0 of phi 0, and then I have my h of I, and then I'm going to have a q of E0 minus H0, and then H of I to the power of n multiplied with phi 0. So let's write out these terms and then start to analyze them and see what we get, okay? So this term, if I then, let's just wait a little bit so people get time to write. If I now write it out term by term, this is going to be equal to phi 0, and then I have H1 of phi 0. So this is first order in the interaction. And then we have plus, and then I have a phi 0. And then I'm getting a term which goes like H of I times Q. So this is an operator, E0 minus H0. And then I have H of I multiplied with phi 0. This is a term which we would call second order, because this is second order in the interaction. So they all have dimension energy because the interaction has dimension energy. We have energy squared divided by energy, so that gives us energy. And then this just continues, and then we would have a phi 0, H of I, and then I have a Q, E0 minus, and then I have H of I, and then I have a new Q, and E0 minus H0, and then H of I, phi 0. So this is a term which we obviously would call third order. And this just goes on and on. I can actually resum these terms, but this is something which we will do next week. But the point now is that we have an expansion here where we now could, in principle, calculate these terms, except that we don't know this quantity here. But we know this one, we know this one, we know this one. So except for that one, this is an expression where we know many of the equations, how to define them. Now, during Wigner perturbation theory, we'll have this dependence on the exact energy. And that is, in a way, a little bit inconvenient. If we want to have a calculation recipe where every order can be determined by known quantities. And that is what Rayleigh-Schrödinger perturbation theory gives us. And that's where we will start next Thursday. So what we see here is that we have a E0 dependence, which is in a way unwanted from a calculational point of view. So the answer to that is what we call Rayleigh-Schrödinger perturbation theory. And that's where we will start next week. And that will give us a practical recipe by which we can calculate these coefficients order by order. You could obviously solve these equations iteratively with a guess for E0, but you don't know whether it converges or not. So next week, we are going to derive Rayleigh-Schrödinger perturbation theory. And when we have the equations for Rayleigh-Schrödinger perturbation theory, we are going to go back to this simple example which we had earlier. That means this example here. And then we're going to see that Rayleigh-Schrödinger perturbation theory is going to correspond to order by order to the different terms which you see here. So this Taylor expansion, which we did, is going now to mimic what we get when we do perturbation theory order by order. Okay, take a small break. And it's the weekend pretty soon. The weather's not supposed to improve, but I guess we can survive that.